Hello there, Mr. Sutton here, bringing you the AB Calculus 6.5 Extra Practice Number 1 solutions on exponential growth and decay. For this problem, we have a radioactive isotope decaying at a rate proportional to the amount present. So that's the key word, meaning this is an exponential function. And since it's a decay function, we're going to write our formula y equals CE to the negative KT, the negative for the decay part of this. All right, so what do they actually want to know? If the decay rate is this percentage per 1,000 years, in how many years will the mass be reduced to 1/5 its initial mass? So we're essentially solving for t. We're asking in how many years. That means we need to plug things in for y, c, and k. Well, out of all of these things, they didn't really tell us the starting amount or the target amount. They did tell us that the decay rate was 43.32%. So we can replace k with 0.4332, and that's at least a good start. Now we do need to do something about the y and the c here in order to solve for this missing t value. So the key is they said, in how many years will the mass be reduced to 1/5 its initial mass? We don't know what the initial mass is. It's some c value, but we know that 1/5 of that initial mass is going to be 1/5 times c, again, whatever c is. So we can write it like this, because when we divide to get rid of the coefficient on the e here, the c is going to go away anyway. So dividing now, that means our c's are going to cancel out. We have 1/5 equals e to all that craziness. To get rid of the e and get t out of exponent land, we need to take the ln, the natural log of both sides. So we can write ln of 1/5 equals negative 0.4332t. And at this point, all there is left to do is divide by the coefficient of t. Let me do that on the calculator. So here we go, dividing this out and pressing enter. That's going to come out to about 3.715. So that's years, but it's not quite years because this decay rate was rated per 1,000 years. So our time units then is going to be 3.715 thousand years, which I guess we could move the decimal over and just call it 3,715 years, but whatever. On this problem, we have some E. coli, which during its exponential phase increases in number at a rate proportional to the current population. So basically, they're saying we have exponential growth is what this is talking about. So let's immediately write y equals CE to the KT. That's our exponential growth formula. And now if the population quadruples in 77 minutes, what's the growth rate? So we're solving for k. That means we need to plug things in for y, c, and also t. So what could we plug in for these things? Well, c is our initial value, our initial number of E. coli, and they didn't tell us that. We did get told that the population is quadrupling in 77 minutes, though. So that means at the very least, time is going to be 77. And if our initial value is quadrupling, I don't know what c is, but I know then that y has to be 4 times c, again, whatever c is. So I'm going to write 4c equals CE to the k times 77, or 77.0k. And at this point, we can divide both sides by c. So we've got 4 equals e to the 77k. Taking the ln of both sides, I can write ln of 4 equals 77k. And at this point, all I have to do is divide by 77 to find my k value. Time for the calculator. So doing that division on there, we end up with 0.018. So that's my k value, but they wanted to know what the growth rate was. So I have to actually, I guess I could leave it this way. This is technically an acceptable version of it, but if I want to make a percentage, make it look cooler, let me move the decimal and call this 1.8%, but percent per what? So this is going to be, let's see here, minutes, right? The population is changing in terms of minutes. So this is going to be 1.8% per minute. For this one, we have a island's population for a period of time growing at a rate proportional to its population. So this is kind of the code word proportional growth here. This is the code word for exponential growth. So that means we have y equals CE to the KT as kind of our starting point, regardless of what else they write here. But now let's see what they wrote. Growth rate is 4.1% per year. Current population is 1,556. What will the population be in 7.3 years from now? So we're essentially solving for y here, the output of this function, and that means that we need things to plug in for C, K, and T. Well, they told us that the K value, the growth rate, was 4.1%. So that's 0.041. And then for the initial value C, that's this 1,556 number. And for time, that's the 7.3 years. So we have 1556 e to the 0.041 times 7.3. And there's the general setup. And now let me actually plug in that time, 7.3. And all we have to do at this point is just plug that in our calculator. This isn't even really an equation we need to solve. It's just evaluate at this point. So plugging that all in the calculator the way it's written. Let me just press enter now. And I'm going to round this off to the nearest person. It seems odd to have like the nearest thousandth for people. So this is going to be 2,099 people. On this one, we have a savings account compounded continuously. So this is going to be exponential growth once you see that whole continuous compounding thing. So I'm just going to start by writing y equals CE to the KT, or you could write even y equals PERT if you're thinking in more pre-calculus terms. If the interest rate is 4.1% per year and the current balance is this amount, and how many years will the balance reach this other amount? So what are we actually solving for? We're asking in how many years. So we need to solve for t at some point. That means we need to plug stuff in for y, c, and k. So for the y value, that's the target amount that I want my money to reach. That's this $1,523.36. And the c value, that's the starting amount, the principal. That's the current balance of $1,148. And then we have e to the kt. So k is my interest rate. That's going to be converted to a decimal 0.041. And then t, we're still solving for that, so we'll just leave that there. All right, I'm going to go ahead and get the exponential term by itself. So let me start by dividing by this 1148 term here. And I'm not going to bother figuring out what that actually equals. I'm just going to leave it as a fraction. We're just going to do everything on the calculator at the last possible minute. Now, to solve for t, I need to get rid of this e to the something function. So let me just take the ln of both sides to cancel out the e. So that gives me ln of this fraction over on the left equals 0.041t. And finally, if I divide this ln by 0.041, that's going to give me my t value. So let me do that piece on the calculator now. So here's what all that craziness looks like on my calculator. I'm just taking the ln of that fraction, dividing it by 0.041, and that's going to come out to 6.8999 and some change. So I guess this would be then, let's see here, 6.900, and the unit on this is going to be years. So there we are. For this problem, for a period of time, an island's population grows at a rate proportional to its population. If we have this proportional to the population stuff, that means we have exponential growth whenever you're growing proportional to the output variable. So we're going to go with y equals CE to the KT is kind of the starting point for everything that follows here. Now, if the growth rate is 2.7% per year, in how many years will the population triple? So we're asking in how many years. That's a t value we have to solve for. So that means we need to plug something in for y, c, and k. Well, I don't know what my starting value is. That would be the c value, and I don't know what my target value is. But I do know that y needs to be 3 times c, because the population has to triple when the growth rate is 0.027. So if I plug in 0.027 for k, I should also be able to write c and 3c, like so here. And at this point, I can cancel out the c's, and then if I want to get rid of that e, I have to take the ln of both sides. So I have ln of 3 on the left equals, and then this is going to be 0.027t on the right side, because ln and e cancel out. Now if I just divide by 0.027 on both sides, that'll give me my t value. Time for the calculator. So I'm going to leave that division in the capable electronic hands of the calculator. Here we go. Press enter. That's 40.689, and that's going to be in years. For this one, we have atmospheric pressure decreasing approximately exponentially as elevation increases. So keyword exponentially and also decreasing. So this is exponential decay. I'm going to write y equals CE to the negative KT, just to give myself kind of a framework to plug things in. So now if the rate of decrease is 12.2% per kilometer and pressure at sea level is 755, and this is millimeters of mercury if you were wondering, what's the pressure at 3.5 kilometers above sea level? Okay, so this is kind of a weird function because this isn't a normal time versus quantity of something sort of input-output relationship. On this one, the input is actually your elevation, and the output is the pressure. So pressure is a function of elevation, which basically means y is going to be pressure, and this T, and also C is also pressure, and then this T value, this is the elevation. So they said, what is the pressure at 3.5 kilometers above sea level? So we're basically asking for this y value here. And we have some initial pressure, and we have some elevation we're supposed to plug in. So let's see what they gave us. Well, they did give us the C value, this initial pressure of 755. And the rate here, that one we're pretty sure about. This is going to be 12.2% that we're plugging in for K, so 0.122. And then for time, that's actually not time, that's elevation. That's going to be this 3.5. So there's our setup. There's what we're going to have to plug in our calculator. Let's go ahead and do it now. So if I plug all that in, I get about 492.6, we'll round it off to 610. And that was the pressure they were talking about, so that's going to be millimeters of mercury. For this one, we have atmospheric pressure decreasing approximately exponentially as elevation increases. So we have exponential decay. That's going to be y equals CE to the KT. One thing we have to be aware of on this problem before we do anything else is that on this problem, the T value, the input is elevation. The output is pressure. Pressure is a function of elevation. So y and c, those are pressure values, and this T value is an input. This is an elevation value. So if the pressure is 772.3 millimeters of mercury in a valley 0.1 kilometers below sea level, and pressure at sea level is this other amount, we want to know the rate of decrease. So we're solving for K, that's the rate of decrease. So that means we need to plug in things for y, c, and t. So y, this is the non-starting pressure value. They said the pressure is 772.3 millimeters of mercury in a valley 0.1 kilometers below sea level. So this is our non-starting value. This is going to be our y value here, this 772.3. The starting value, by which they mean the value at 0 kilometers at sea level, is going to be this 763 value. And then we're doing e to the negative k times, we have an input value of 0.1 kilometers below sea level. That's going to be negative 0.1. All right, so doing all of this, we need to solve for k at this point. So one step I need to do is divide both sides by this 763 to get the e term by itself, the exponential term alone. And I'm also just going to clean up these signs here and just write this as 0.1k in the exponent. So we have 772.3 over 763 equals e to the 0.1k. And now to get rid of the e, I can take the ln of both sides. So I can write ln of this fraction over here, which I'm not going to bother doing on the calculator yet. That's going to equal 0.1k. And now let me just plug this into the calculator, dividing by 0.1. So doing that on the calculator, that comes out to about 0.121, which is to say we have a decay rate of about 12.1 per kilometer, percent per kilometer. For this problem, we have some E. coli increasing in number at a rate proportional to its current population, basically exponential growth. So I'm going to write y equals CE to the KT just to get started on this. If the population is 129.2 million 7.8 minutes ago, and the current population is 162 million, in how many minutes will the population reach 199.6 million? Well, it certainly seems like there's too many numbers here. What are we ultimately asking for? We're saying in how many minutes. So we're asking for a time unit. So that's the t value here that we eventually need to solve for. And we need to solve for it by plugging in something for c, y, and also k. So what do we have right now? We have a whole bunch of y and c kind of candidates here, but we don't really have anything for the k value. And the interesting thing is they gave us this 7.8 minutes, which seems like it's a t value, but it's not the t value that we need. So our first goal on this is going to be to solve for the k value. This is kind of a two-step problem. For the first step of the problem, we actually have a t value, and we're going to have to find a y and a c that go with it, and we're going to solve for k. Once we find k on this first part of the problem, we're going to use it on the second part of the problem to figure out this t value they ultimately want us to find. So, if the population was 129.2 million, so that's a y value, and that was 7.8 minutes ago. So that's like a negative 7.8 for t. And the current population is 162 million, so that's our c value. So let me put in e then, e to the k times negative 7.8. This is basically saying 7.8 minutes ago, the population, which at time 0 is 162, was 129.2. So this is going to be enough for us to solve for this k value. So to start solving for this, let me divide both sides by 162. And I'll also make this just negative 7.8k just to make it look nicer. Now to solve for k, I have to take the ln of both sides to get rid of this e. So we have ln of this fraction equals negative 7.8k. And let me divide by negative 7.8 now to get some kind of k value. So on my calculator, dividing that, I get roughly 0.029 and some change. Now I'm going to be using this value later on, and I want to be as accurate as possible, and I don't feel like writing it. So I'm actually going to store this k value as some constant, which I'm going to call a, which is, again, approximately 0.0290 and some change. And I'm going to do that on my calculator as well. So let me go to store, and then we'll do alpha a, enter. There we go. So now I can just reuse that whenever I want. So back to the problem, we want to know in how many minutes will the population reach 199.6 million. So now I'm turning around and solving for a t value. This time around, we've got 199.6 as my target value, as my y value here. Our current population is still 162. That's the initial condition, so to speak. This time around, though, I don't know t, but I have this k value that I set equal to a. So I'm going to write e to the a times t. Solving for t this time around, I'm going to pretty much use the same steps I did up here. I'm going to divide by the 162. I'm going to take the ln of both sides. That'll get rid of the e, and that'll just leave me with a times t on the right side. This time around, I'm going to divide the ln of this stuff by a, and I'll do that on the calculator. So here we are back on the calculator. I have ln of that fraction divided by what I just stored as a, and pressing enter, that's about 7.196, and that is going to be in minutes. Years? No, minutes. There we go. Now we're nailing those time units.